to discuss about the Monte Carlo simulations application when we are trying to find out the solution, or rather the area under a curve or a volume enclosed by a surface. Okay, so as we have previously discussed, the Monte Carlo simulation is a probabilistic method, and finding area enclosed under a curve is of deterministic behavior. So here we will see how we use this probabilistic method or simulation programming so as to find out the area under a curve. Okay, so first and foremost of all, what we do here, suppose what we have to do, we want to find out the area. Say suppose the area is bounded by the curve y equal to fx. Okay, so just consider y equal to fx is the curve given and x axis is the another boundary. So that means we are just working with, suppose with say this figure actually I am drawing here separately. So this is your curve y equal to fx. Okay, and you are supposed to find out the solution lying between say x equals to a and say, let me extend it, x equals to b. So this is the thing we are trying to find out. So one thing is very clear, you can obviously find out this area either directly if y equal to fx, that means analytically we can find out if y equal to fx is not a complicated curve, we can simply find it out. But if it is a complicated curve, then we will see later in the numerical methods we take help of trapezoidal rule or any numerical integration formula. Okay, so what we are doing here, those methods, the numerical methods are actually deterministic methods. Okay, but here we won't be using any deterministic method. Rather, we will be showing a probabilistic method or probabilistic simulation method rather can also be used for this type of problems. Okay, so what actually we will do, let us just see what they are saying here. First and foremost of all, this y equal to fx is already supplied to us. Okay, and x running over the interval a to b is already given. Okay, and it is also said y is some given, y equal to fx is some given continuous function. So that means what we are assuming this function is well defined, it is smooth and no problem with its analytical definition. Okay, we are not considering any problematic curve. That means whether it is discontinuous or whether it is having some steep rise or steep decrease or steep decline, we are not taking all those into consideration. We are taking this to be a well behaved function. Okay, now let the function be bounded. Okay, so for just sake of simplicity, we are taking the function to be a positive value. That means fx lying within this range, greater than equal to 0 and less than equal to m, where m is the upper bound. Okay, whenever x is running within the interval given, so a to b. Okay, now the situation is like this one, what they are saying here. This is the curve, as I said. So this fx is less than equal to m. That means what is m? Y equal to m. If I take like this is here y equal to m, this up to this amount, so y equal to m. So now if you just consider a rectangle with breadth b minus a and length m, that means actually you are considering this rectangle, this length b minus a and this amount of length m. Okay, so you can consider this rectangle, and then what we will do, we will select a point p xy at random. Okay, so that means without any specified pattern, we will be selecting a point, okay, within the rectangular region. If I call the rectangular region capital R, we will be selecting at random points from it. Okay, so that means what? Say suppose I am drawing it here separately. You are taking say 1 point, 1 point, 1 point like this. We are just randomly choosing points. This randomly choosing points means what? This, whenever you choose one point, say p of xy, it is specified by the abscissa and the ordinate. So actually whenever I am saying I am randomly choosing a point, that means what? I am randomly choosing x and I am randomly choosing y. Okay, so randomly choosing x means what? It is chosen from a to b, any random number is chosen. Now we have discussed before how can we generate random real numbers, that means the sequence of real numbers. Okay, so actually you are creating two sequences here, one corresponding to the abscissa, another corresponding to the ordinate. Okay, so that means one along x-axis you are choosing a random number sequence, and along y-axis you are choosing a random number sequence. Okay, so for each x and y pair you are getting 1 point of the another. Okay, so once we are choosing like that, what will happen? Ki we are restricting, we are choosing the random number such that x is lying between a to b and y is less than equal to m and greater than equal to 0. So this thing we are choosing. Okay, so these are the boundaries of y and these are the boundaries of x that we are choosing. Okay, so once we are choosing like that, where will my p lie? P will definitely lie in this rectangular region. Okay, p will definitely lie here, anywhere here, but in some cases the p might lie or may lie rather below the curve y equal to fx, or it may lie somewhere here. Okay, but what is our main motive? Our main motive is just to find out this area enclosed by this curve. So the favorable event for that is occurrence of p below the curve, because if p is occurring below the curve, that only is contributory to find the area enclosed by this curve. But suppose if my p is lying here, this is not a part of the area enclosed by the curve, so that will not be adding up to the area, because if you just consider what is this area, it is nothing but the collection of points which is lying within this region. What is this region? This region is bounded by the fact it is lying below the y equal to fx curve and lying above the x-axis and bounded between x equal to a and x equal to b. This is actually what we mean by the area enclosed by the curve. It is nothing but a collection of points. So now what we are doing, we are generating randomly some points. Now what is our task? To observe whether the point is lying inside the area required or outside the area. Depending on whether it lies inside the area or outside the area, if it is lying inside the area, then that contributes some credit to the area we are trying to find out. If it does not lie, then it is not contributing anything to the area we are trying to find out. So depending on that, we are getting actually two counts. Okay, what are the two counts? One counts is C1 if I say, and C2. Okay, so as soon as I generate one x and one y, say x1 y1 and generate. Okay, let me change it a bit. So as soon as I generate x1 y1, 1 point I generate p1 x1 comma y1. Okay, so obviously I am generating something from this curve or something within this rectangle. Okay, this length height m and this breadth b minus a, so I am something getting 1 point from here, say p1. So as soon as you are getting a point from here, so that means I count it, say 1. Now we will check what the random point which is generated, whether it is lying inside the curve, that means whether it is lying below the curve or not. So let this be my curve. So if it is lying inside the curve or below the curve rather, then okay, I will put 1 here, so as to just specify okay, this point is a point lying within the required area. Okay, now we consider another point generated randomly, p2. So suppose p2 is lying here, so again p2 is lying inside this rectangular region, so this will become 2 now. Okay, but it is lying outside this area, so it will remain as it is, so 1. Okay, similarly we will go on generating many points and we will go on just putting c1 equals to some plus 1 and c2 equals to plus 1. Whenever my point is lying within the rectangular region, if I will put c1 equal to plus 1, and whenever that point is lying below the curve, we will put c2 equals to plus c2 whatever value it is having in the last stage plus 1. Okay, so suppose another point is take say p3, it is again lying in this region, so for p3 this becomes 3, and p3 as it is lying below the curve, so this becomes 2. So ultimately this goes on, and suppose at the last stage you are getting n as this one, 4 5 6 up to n, say when n is finite, that means the real number I am taking, and here it is small n, suppose last one which is taking. So last one actually gives what, the addition of all the points which are accumulated below the surface or below the curve, and capital N denotes the accumulation or adding up all the points which are lying inside the rectangular region. Okay, so the frequency will be given by n by n, just like they have done here. So area under the curve is nothing but the collection of the points lying below it, below this curve. By area of the rectangle is nothing but the points lying inside the rectangle, is approximately equal to number of points counted below curve, that is this is your count C2, and total number of random points, that means this is your count C1. So that means whatever I have given here, it is capital N, small n by capital N, small n by capital N, according to whatever notations I am using just now, just here. Okay, so one thing is clear, ki the idea of the definition, frequency definition of probability. In probability, what do? We collect all the events and we collect the favorable events. Then what we do, we find out the ratio between the two. And what we do, say ki because of statistical regularity, if we go on increasing the number of independent trials, that ratio will ultimately converge towards the required probability of the event. So exactly the same thing is used here, same concept is used here. What we are trying to find out, area under curve. That's why I am taking area under curve and area under rectangle ratio. But if you go on increasing the number of random points, here number of independent trials corresponding to number of choosing of random points. Okay, so the more random points you choose, the better and better accuracy you will get. That's why there, instead of equality, we are given here the approximately equal sign, like this. Okay, so area under curve by area of rectangle is approximately equal to the ratio generated by number of points counted below curve by total number of random points. Okay, so this is a strategy. Now if this is a strategy, where is the probabilistic behavior? The probabilistic behavior lies exactly where you are choosing the points randomly. And we know how can we choose random points. As I already said, we have to choose the abscissa and the ordinate randomly. That means we have to perform random number generation twice. Once along x-axis lying between A and B, another along y-axis lying between 0 and capital A. Okay, so once you do that, corresponding to each pair of abscissa and ordinate, you are getting or generating one random point, and that is contributing in this area or in this ratio calculation. Okay, so whenever we are saying we are generating random numbers, we know some of the methods, exactly two methods we have learned. Any of those can be used. Okay, so here lies the Monte Carlo simulation algorithm for this one. Let me just go to the algorithm directly. So whenever one tries to write any program, that program should be based on this algorithm. So what is it? Very clear. Key input is what? Total number n of random points to be generated in the simulation. That depends, and one user can generate say 10,000 points, another can generate 10 to the power 4 points, another can generate 10 to the power 6 points. It depends on the user. Okay, and also on the computing machine you are using, how much memory it allows, okay, or it has rather, to deal with the data points you are giving it. Okay, so total number n of random points will be generated in simulation. So here, according to this notation, the notation I have used is should be n by n. Okay, so whatever, small n is the total number of random points, so this one. Okay, area equal to approximate area of the specified curve y equal to fx over the given interval. So this is the interval. Acha, then this should be coming as a neat output of the algorithm once we run. The approximation of the area required should be coming out. Okay, acha. And what are the boundaries of the area? Y equal to fx curve, where fx is itself bounded by this 0 and m, and x bounded between a and b. So what are the steps of this? Actually is the starting of the algorithm procedure with the input this one. Key initialize counter equal to 0. Okay, so what is actually counter equal to 0? Counter corresponds to the C2 I have shown here. It will be counting on the number of points which is lying below the curve, because that are actually favorable event points corresponding to area calculation. So we will calculate those points only. And whereas as this is fixed, so C1 here is fixed equals to small n, so it won't be counted anymore. Okay, so initial is counter equal to 0. So first and foremost of all, I have not taken any point till now, so obviously counter equal to 0. Now for I1 to up to small n, that means for each point I will be checking something. What I will be checking? Whether the point I have chosen randomly is lying below the surface, below the curve, or above the curve. Okay, so for I1 to n, that means for each of the randomly chosen point, I have to do or repeat steps 3, 4 and 5. What is the step 3? Calculate random coordinates xi and yi such that xi lie within this range and yi lie within this range. As I already said, you have to generate two random sequences of real numbers, one corresponding to axis and another corresponding to y coordinate, along with the restrictions ki axis xi should be lying within AB and yi should be lying within 0 and m. Once you calculate this, definitely now you can put this xi in the function because f is fixed and it is already provided to you. Okay, so I can put it here so as to get f of xi. Acha, now what I will just check now, ki if yi is less than equal to fxi, because yi is already generated from the random generation. Okay, so if yi is less than equal to fxi, then what? Then increment the counter by 1. Okay, why? Because yi is what? Yi I am taking somewhere here, that means corresponding to one point p yi is taken. So suppose I rub this all out, yi is taken corresponding to the point you are choosing, right? Achha, now if I am choosing it corresponding to the points, yi is corresponding to the point pi say xi comma yi. Okay, now f of xi, here also I am using the random sequence only, but along with it a fixed function is used. This is already given. Okay, so now what we are supposed to see, ki if yi is any point here, or rather let me just show it separately. So suppose this is your yi and this is your f of xi, then what? Yi greater than f of xi means what? Your yi is lying above the curve, that means yi is not contributing to the area inside the curve. Okay, so the yi should not be coming in the counter count, that means counter in the counter increment. Okay, when it will come? If suppose yi lies here, so suppose I have chosen one point say p1 such that x1 y1 lies inside here. Okay, as soon as it lies here, y1 is this much, but what is f of x1? F of x1 is this much length, and y1 is this much length. So this here y1 is less than f of x1. That means what? The point is lying below the curve. That means what? This point is contributing towards the area calculation, so that will be considered in the counter. So that's what they're saying. If yi less than equal to fxi, even if it is lying on the curve itself, so equality is considered here. If yi less than equal to fxi, then increment the counter by 1. So here you will put counter equal to counter plus 1. Otherwise leave the counter as it is. So there is a if loop running here. If yi less than equal to fxi, then counter equal to counter plus 1. Otherwise it remains as it is. Okay, then once you do this and calculate, so these 3, 4 and 5 are the repeating steps. So once this repetition is done with for each and every of the point we have chosen, or randomly which is generated, not chosen but randomly generated, whatever. So ultimately we calculate the area. How we calculate the area? Using this formula. What is the formula saying? Ki area under the curve equal to, or approximately equal to, area of rectangle into this ratio. So area of rectangle is what? M into b minus a. And what is this ratio? The numerator is nothing but the counter here, that is the C2 count as we said, okay, by the total number of points, that is small n. So this thing, so this one because of the ratio and this one because of the area of the rectangle, then you stop the program, so and output the area. Okay, so this is the whole Monte Carlo algorithm. And where is the probabilistic nature? Where you are generating the points randomly. Okay, acha. So So Monte Carlo technique is probabilistic and typically requires a large number of trials before the deviation between the predicted and true values becomes small. That's what I have said repeatedly, ki because of the statistical regularity, you have to repeat the number of trials. That means you have to choose the random number of points as much large as possible, so that this is not exactly equal to, so this approximation or approximate result gets better and better accuracy. Okay. Another thing is that the actual area, suppose the curve they are considering y equal to cos x over the interval x lying between minus pi by 2 to plus pi by 2, and cos x obviously lying between 0 to 2. Though it should be taken as 1, okay, whatever they are taking it to be 0 to less than 2, strictly less than 2. Okay, so for this one, if you try to calculate the area will come out to be 2 square units. You can simply just find out the area by what? Minus pi by 2 to pi by 2 cos x dx. This will give you the area. Okay, so this is a very trivial example, so you can directly calculate it, and this turns out to be 2 square unit. Okay, but instead of following this analytical method, if you use the Monte Carlo simulation algorithm, then the values are given by, let us go into the next page, this table. You can see the approximation to area. If you take 100 points, this is the value, this is coming by the Monte Carlo simulation. If you take 200 points, this is the value coming, and all these are showing like that. Okay, so as you can see, if I go on increasing the number of points, 2 is the original value which should be obtained, because analytically 2 is coming, so it is deviation, you can see. Okay, so the more you increase the number of points, see, this is the least deviating from 2.011, this or this is the least deviating. Okay, again this also. So once you cross some certain limit, obviously the deviation goes on decreasing, or rather oscillate. Here it is oscillate within a small range. So whatever, the main thing we are trying to focus, if you consider this one, say 100 trials with 3000 trials, you can easily see the change, or you can easily say how much smaller the deviation is. Here it is 2.07, so 2 minus 2.07 mod is 0.07, but here it is 2.011, so it is much lesser than 2 minus 2.011, so smaller error is coming here. So that is it. If you increase the trials, obviously the error is going to decrease. Okay. And another thing, instead of using the Monte Carlo simulation method, we could have used any numerical integration procedure rather, such as the trapezoidal rule, Simpson's one-third rule. Those are all deterministic procedures. There also you will get some approximation result, and obviously in that case we are not using any random number generation. Okay. Now similarly you can just see the volume under the surface. The same thing, only we are now increasing one coordinate extra. That means instead of working in the xy plane, we will be working in the xyz 3D space. Okay, so let this be the particular example is given. So this be the sphere less than equal to 1, which we are considering the first octant only, where all 3 are greater than 0. That means this one, this shaded region. So what we are now supposed to do, exactly the same what we have discussed above, only a bit change. Key 1, instead of curve, now the points are to lie below the surface. This is the surface, so the points are to lie below it. One change. Another, you have to generate here 3 sequences, 3 real number sequences instead of 2. One for the x-axis, another for the y-axis, another for the z-axis. Okay, then again the same thing. If it lies below the surface, you count it as a favorable event. If it does not lie, then remain as it is. Okay, and this is the total number of random points you are generating. So this volume under surface by volume of box, instead of this rectangle, what you will get now, a parallelepiped. Okay, so instead of this, either the point will obviously lie within the rectangle, because we are choosing we are setting the random number generation like that, ki my xi lies within the specified range, my yi also lie within the specified range, and zi also lie within the specified range. So within rectangle is obvious, but if it lies below the surface, then only we will count it, otherwise it will not be counted. So following the same procedure, we can give the Monte Carlo simulation algorithm. Total number of endpoints is your inputs. volume you have to output, which is approximate value enclosed by the specified function z equal to fxy in the first octant. That means x greater than 0, y greater than 0, z greater than 0. So these are the restrictions which are to be satisfied. Okay. Again we have to initialize the counter, and for I 1 2 up to n, that means whatever points you are chosen, for each of these points you have to repeat the steps running from 3 up to 5. Okay. So again the same thing, you calculate the random coordinates xi, yi, zi, such that xi lie within this range, yi line and zi both, that is all of them are lying within 1. There is unit length in all directions. Okay. Or you can take a, b, c, d or 0m. Okay. It doesn't matter, it will be whatever it is asked in the problem, you have to follow that. Okay. Then calculate f of xi, yi for the random coordinate xi, yi. Okay. And if random zi is less than or equal to f of xi, yi, that means zi is lying below the surface, and if it is not, then it is lying above the surface. But we want that to lie below the surface, so we will add counter equal to counter plus 1 if it is lying below the surface. Here it will be increased, then otherwise leave as it is. Okay. So these steps are repeated. So once these steps are repeated, you are getting the total number of counter equal to, suppose you are getting, say, capital C I name. Okay. Then what you are getting as a volume, m into d minus c into b minus a. So this for the x axis, this for, say, y axis, and this for z axis. That means here again you are using this formula, volume under surface equals to volume of box. So volume of box, for volume of box only you are getting this first part. Okay. And this counter by n, counter because of this how many number of points are lying below the surface by total number of points. So quite clear or obvious from here how we are getting it. So output the volume and then stop the program. So this is your Monte Carlo simulation algorithm for counting the volume enclosed by a surface. Okay. So again using this thing, similarly you can calculate it directly, or you can use this approximate Monte Carlo simulation method so as to generate the solution. The actual volume is this one, 0.5236, and you can simply see if you go on increasing the number of turns, then only you come very close to this 0.5236. Otherwise if you just use 100, see the deviation, 0.47 is coming as the answer, whereas the actual answer is 0.5236, but you are getting 0.4700 for this one, first one. Or again for 200 also the deviation is huge. The deviation decreases in fact when you are getting greater than 10,000, greater than or equal to 10,000. You can see the deviation is decreasing. So this is it, this is the idea. Okay, so let us stop here.